Hey boys and girls, welcome to another video lecture. Today we're going to be working on modeling exponential and power functions. This goes with section 8.7 in your textbook. And what you should be able to do today, and I know this list looks kind of long, but it actually is going to go rather quickly. These all go together here. We're going to write an exponential model given just 2 points. That's going to be by hand, no calculator. And then we're going to be given many data, and we're going to use a calculator to write an exponential model. We're also going to do those two same things with power functions. We're going to write a power function given 2 points, and we're going to write a power function model given many data, and again, that's on the calculator. And while we're doing this, particularly on the calculator, we're going to determine at least once which model is best. Is exponential better than power, or is linear a better possibility? And we'll talk about when do we get to make a choice? Okay, so let's do a quick little review here on what's the difference between an exponential function and a power function. So I need you to think about that for a second. Pause it and think about, what does an exponential function look like? What does a power function look like? Okay, an exponential function has this basic form of y equals ab to the x. Our x is in the exponent, hence an exponential function. Now we've talked about the shifting, the transformations up and down, the vertical stretch and shift, and we've even changed that base so it's stuff like 1 plus r or 1 plus r over n. We've seen all those, but our basic exponential function looks just like this, or y equals ab to the x. Okay, power function, very similar looking, except it's y equals ax to the b. So this is something more like a quadratic, y equals 3x squared, would fit that model. Maybe something like a quintic, y equals maybe the negative 4x to the fifth. Those are all power functions, as opposed to, our exponential, something like y equals 3 times 2 to the x would be a power function. So different looking models, in the graphs we know look quite a bit different. Or I guess a little bit different, maybe not entirely different. Okay, so let's go work towards our first objective here. We're going to write an exponential function in the form y equals ab to the x. And the graph is going to intersect the points 1, 6, and 3, 24. Okay, here's what I suggest you. First of all, I'm going to rewrite the function in our very general form. And what I'm going to do here is I'm going to substitute each of these 2 points, 1, 6, and also 324, into that basic form, y equals ab to the x. I'm going to do it separately. I'm going to do it twice. I'm going to get 2 different equations. Here's my suggestion. You find the point that's going to give you the largest exponent. In other words, in this case, which one has the larger x value? Well, that's 3, 24. So choose points. You should definitely write this in your notes. That will make or that will have the larger exponent. And there's a reason why I'm having you guys do this. It's going to look a lot nicer when we go ahead and solve this. It's going to be a lot easier. We're not going to end up with any negative in the exponents when we do this my method. Okay, so I'm going to take the point 324. So 3, 24. And I'm going to substitute in. So 24 equals a times b to the x, and x is 3. So notice here I have one equation, I have 2 variables. Okay, that's fine. I'm going to get another equation from 1, 6, and I'm going to put it right underneath the equation I just wrote out. So I'm going to use the point 1, 6. 6 equals a times b to the 1. And now what I have here is a system of equations. This is not a linear system of equations. We have not seen how to solve this yet. In fact, that's what we're going to do today. But I certainly have 2 variables, 2 equations. Here we go. Here's how we solve this. So here's why I lined this up, and here's why I want my b cubed on top of my b to the 1. The way that I solve this is by division. And I have this all lined up. I just need to put my division bar there. Look what happens when we divide. On the left side, I get 24 divided by 6. Oh, that's nice. Mr. Chetland chose some nice numbers for us. Okay, so 24 divided by 6. Okay, what happens with the a's? Well, I have a to the 1 over a to the 1. Those simplify, right? I get just 1. Okay, great. So that's just a 1 out there. Well, you can not write it in if you want to. I'm going to put it out there so you can see it. Okay, and now what happens with our b's? Well, I get b to the 3rd over b to the 1. I subtract those exponents, right? I get b to the 3 minus 1, or b squared. And because I chose to have my higher exponent up top, I'm always going to end up with a positive exponent in this next line that I just wrote there. So that ends up to be really nice for us if you make that decision. Okay, so I end up with b squared equals 4, or b is going to take the square root of both sides, and I get, I really should get plus or minus 2, but I'm going to throw out the negative 2 because I don't want my base b to be a negative value. So I'm recognizing that it should be plus or minus, but I'm throwing out the negative there because I don't want it. Okay, so I now have b. I also have a lot of stuff in the way up here. I'm going to clean all this up as best I can. Okay, and I'm going to take that. Basically, I'm going to do substitution now. I'm going to take b equals 2, and I'm going to put it into one of these two equations up there, either the green or the red one. There's a good choice and there's a not so good choice. Which one's easier to plug into? Well, I would plug it into the second one, the red one, right? I mean, look how much easier. This has a b to the 1, and even the 6 is less than 24. So you might want to plug it into that second equation, but it certainly doesn't matter. And I'm going to do a little work on the side here, and I'm going to get 6 equals a times 2 to the 1, or in other words, a equals 3. So I've solved my system. I have A, I have B. I just need to put my final touches on this, and I'm going to write it out like this. This is the form that we're using, the y equals ab to the x. And I'm going to put in 3 for A, 2 for B to the x. And that, again, we leave it just like that. I cannot combine that. This does not equal y equals 6 to the x. Right? I can't do that. I'm not allowed to do that. So I just get y equals 3 times 2 to the x. And that's how we solve our for an exponential function given 2 points. Okay, let's take a look at, actually, excuse me, I'm going to let you guys do this one on your own. So take a moment. The numbers aren't quite as nice, but take a moment and solve this one, and I'll put the solution up here momentarily. Okay, so I get A is going to be a half. B, which is probably what you got first, ends up being 8. So the equation ends up being y equals 1/2 times 8 to the x. Okay, so there's a little practice for you with writing exponential functions given 2 points. And now what we're going to do is, and you need your calculator for this one. Sorry I didn't mention that before. We're going to take this set of data, this table here, and this is data for the number of cell phone subscribers from like 88 to 97. I'm just reading the question here. T is the number of years from 1987. We're going to plot these points on the calculator, and we're going to use the regression feature on our calculator it's going to calculate for us the exponential model, and it's going to show us how good it is. We can actually graph this and take a look at it as well. So we'll say besides just plotting the point, we're also going to use the regression feature. We're going to use the exponential regression feature for this data. So what you need to do is grab your calculator, and you might want to write these steps down. I need to quit out of this first of all. Okay, I'm going to go into stats. So the first thing I hit is stats. And then the second thing I'm going to hit is, I'm just going to hit enter, which it should say edit. Okay, so I'm just going to hit enter now. And you're going to see L1, L2. You probably have other data already there. I've already put in this data. So you might want to take a moment here and enter the data. This goes from 1 to 10 on your x's. So that's going to go down all the way down to 10 over here. 7, 8, 9, and 10. And then the right column is going to be all your outputs, and there's all your outputs there, 1.6, 2.7, and so on. So you're going to enter all that data into your L1 and L2. So step 3 here, enter inputs into L1, outputs into L2. Okay, what do we do from here? Well, I'm going to go ahead and see what this thing looks like. So I'm going to, I'm going to make this a big screen for you here. Okay, so right now if I go to my graph, in fact, if I go to my y equals, I have this other function in there. I'm going to clear that off. You don't want anything else in there. We're going to see just the data. And if I go to my graph, nothing special is going to happen. I got nothing showing up right now. Okay, that's because I didn't turn on plot 1. If I go back into my y equals, see up here where it says plot 1, see how it's, whoa, all right. See how it's not highlighted? Well, what I need to do is go up there and highlight it. So I'm going to go up to plot 1, and I'm going to hit enter. And now when I go off it, now it's highlighted. And so it's turned plot 1 on, and it's probably already by default going, it's now going to go look at your L1 and L2 points, and it's going to plot them. Now those points are rather high up, right? If I go to my graph, I'll probably still, well, I do see some points. I don't see that many. But here's a little trick for you here. If you go into zoom, and if you push down, and I think it's number 9, might be 0 though, I think it's 9. Yeah, it's number 9, there it is. See where it says zoom stat? It's going to go look at your statistics, right, that you have in your plot 1 that's turned on, and it's going to give you at least a decent window for the statistics that you have turned on. So I'm going to choose number 9, and now I can see all the points. And now I can see the shape of this thing. So and I've got the shape that, well, it looks like it's doing something like that, right? So it looks like it's a pretty decent exponential model, doesn't it? Okay, so that's just a look at it, right? I haven't really done anything numerically. I just put the numbers in the graph, and now I'm looking at them. Okay, I'm actually going to now run the regression model. So I'm going to go back to our list here and make a little bar here. So to run the regression, so I'm going to go back to step 1, and I'm going to go back into stats. And I'm going to go over to, I think it says calc, not calc. I think it says calc. Maybe even says calculate. So if I hit stats, and I'll go right over to where it says calc. And I want to go down far enough, and I'm going to see eventually exp reg. There it is right there. Oop, went a little too far. There's power reg. We're going to do that in a few minutes here. There's exponential regression. It's number 0. Okay, so I can hit enter, or if I just remember it, I can just go ahead and hit 0. And on my calculator, my screen looks like this. If you have a newer TI-84, you might have a slightly different screen. If I want to go ahead and calculate, I'm going to go hit enter, and it's going to do its thing, whatever calculations it does, and look what it did for us. It found our A value, and it found our B value. Just like we did before with 2 points, it's doing it with 10 points. And there's our function. I'm done with that part of the problem. Y equals, I'm going to grab a bunch of decimal places, 3.00. I might even grab the 7. Actually, that rounds up to 8. And then times B, which is 1.459 maybe, to the x. There's my model. It did the work for me. We're going to do the same thing later on with a power regression, but it's all the same steps there. So that's going to go a lot faster for us. But there's all the stuff that we need. Okay. At this point here, you might be saying, hey, Mr. Cheller, I don't have these r and r squared values. In particular, I'm going to look at a couple decimals of this r squared value. When that's close to 1, see how r squared is like 0.9935349? That's really close to 1. That means that our model works really well with the data. So this is saying that this exponential model is going to work really well. I can go ahead and graph this. I can put these numbers in there, and I can take a look at it. In fact, I'm going to go do that right now. Okay, so I typed in my function, and I put in a bunch of decimal places. And I'm going to go ahead and graph this now. And as we see, here goes my function, and it's basically hitting like all these points just about spot on, right? Oh, it missed that last one. Just when I said it was about hitting them all spot on. But it wasn't perfect, right? That number, r squared, wasn't close to 1. Excuse me, it was close to 1. It wasn't exactly 1. So it was pretty darn close, but not exact. So if you're not getting that r squared value, I'll show you guys in class. exactly how to get that. We just need to do it once and you'll be set. But I'm going to wait till class and not waste time in our video here. Okay, let's move on then. So we're going to do similar types of questions, and now we're going to do the same. We're going to do this with a power function. So now we're using the y equals ax to the b as opposed to the y equals ab to the x. This again was exponential, right? So now we're working with the power function, so slightly different model. But the setup's the same. I'm going to do the same thing. The way I'm going to solve this is going to be just slightly different. So I'm going to still grab my y equals ax to the, or my power function this time, and I'm going to put in my values, and I'm still going to put in my larger term first. And what I mean by that is put in, we want our base, our x value to be larger. So put in larger base first. It's usually going to be the case, at least on these nice ones, where the base and the y value are both larger than your x. It certainly doesn't need to be though. Okay, so let's go ahead and do this. So I'm going to put in 324. Okay, so when y is 24, this is going to equal a times 3 to the b. And now I'm going to put in my other point, which is 1, 6. And I'm going to say 6 equals a times 1 to the b. Okay, so somewhat similar looking. And again, I wrote it one right on top of the other, and the process is the same. I'm still doing division here. Isn't this nice? I'm still going to divide the left side of the equations and the right side of the equations. So when I do that, I get 24 over 6 is still 4. And, oh, look at this. The a's still cancel. Okay, now what happens with the 3 to the b divided by 1 to the b? Well, they're both to the b, and they're always going to be both to the b, right? Because we can't start with the same equation. So I'm going to write this as, and I know we can just write it as 3, but I want to show you where it comes from. Right, 3 over 1 to the b. Okay, so now how do we solve this equation? I'm going to rewrite this. 4 equals 3 to the b. I want to get at the exponent, right? I want to unwrap and get at the exponent. So how do we unwrap exponentiation? Ooh, that's something recent, isn't it? This is logarithm. I'm going to take the log of both sides. What base would you like to use? Well, what base do we have in the problem? Well, we have base 3, don't we? So it makes sense to do base 3 of both sides. In the I, you're looking at this right side here. What's a logarithm of 3 to the b base 3? Well, the log 3 and the 3 cancel, don't they? And we're left with a b. And that's what we want, right? We want to get b by itself. So b ends up being, and there's no way around this one here, the log of 4 base 3. Okay, so we got b. Now we also want to go and grab a. I would suggest if you're doing this one on your own, that you put this in the simpler equation. I would probably choose this one here. Because I can do 1 to any power, and I know it's going to be 1. However, I'm going to do this with the more difficult one so that you see it done like that. Because we might not always have 1 as our base there. So I'm actually going to choose the 24 equals a times 3 to the b. And you're going to see this actually works out, believe it or not, actually works out beautifully. Okay, so 24 equals a is what I'm looking for times 3 to the, look at what we have here. Log base 3 of 4. Ooh, ooh, ooh. Isn't this nice? We have 3 to the and log base 3. Those unwrap again. Isn't that wonderful? When we get 24 equals a times 4, don't we? Okay, I can unwrap that, a little division. I get a equals 6, and everything is right in our world. And I can go ahead and write this equation. But this, I wanted to show you this other, the harder way of doing this, all this stuff here, because that's often going to be the case where we don't have a base 1 like we do in that black equation there. Okay, so I have a, I have b. I'm going to go ahead and write this equation now. And we had what, y equals ax to the b, right, our power function. So we have y equals 6x to the log base 3 of 4. Kind of a weird looking answer there, but hey, that's what we get. It's not always pretty, folks, but that's what we get. Okay, so folks, take a minute here and try this one on your own, and pause it here. I'm going to put up the solutions. Okay, I get that b is going to be log of 3 base 2, and a ends up being 5/3. So that means your function is going to be y equals 5/3 x to the log of 3 base 2. Lovely little solution there. But again, not always pretty. In fact, it can be much worse. But I'm making these up so that at least the it cancels a little bit along the way with the log of base 2 to the 2 to the 3 or something like that. It works out kind of, or 2 to the log of 3 base 2 cancel out kind of nicely. But anyways, yeah, these can get kind of nasty, but not for us. Not for us. Okay, last bit here, and then we'll call it a day. So let's go back to that same data we had before, and this time we're going to write the power function. So I don't need to edit or add anything new to my calculator. I'm just going to bring it up. I'm going to go back into my stats. All the data is already in there. So I'm just going to go over to calculate now. And instead of going down to exponential regression, guess which one we're going to choose for our power function? Somewhere down there should be, you got it, power regression, right? PWR reg. There it is, A. So I can go ahead and hit enter here. And I'm going to hit enter again. And again, it's going to give me my A value, my B value, and if you have the your diagnostics turned on, again, if not, I'll show you this in class tomorrow, it's going to give you your R squared value. Notice here that our R squared value is just 0.94, where with the exponential, the R squared value was 0.99. So this R squared value is not as close to 1 as the exponential is. So that means the exponential function is going to be a much better fit with our data. So I'm going to go ahead and write out my function here. Y equals, again, 1.045. I think that's enough to graph for decimal places, times x to the 1.519. So again, I would contend that because this R squared value is not as close to 1, right, it's 0.94, it's not as good of a fit. So I'm going to take a look at that graph real fast. Okay, so here I am typing my function 1.04508 times x to the 1.519. Again, I'm just putting in several decimal places. I'm going to go to my graph. Here comes my power function, and it's not quite as good, right? It's pretty decent. Oh, it's actually starting to go way off over here, isn't it? Starting to get off track a little bit there. It's pretty decent, but it's certainly not as good as the exponential function is. So that's a way to determine, that's how you want to determine which one's best. It's by the R squared value. So we'll take a look at that in class tomorrow, particularly for those who don't have it on their calculators quite yet with that R squared value. Okay, did we do all these things? Did we write an exponential model given 2 points? Yes. Did we do it given data on the calculator? Yes. Do we do the same things with a power function? You betcha. And did we determine which is more appropriate, exponential or power function? And we didn't look at the linear, but we're also going to look at a linear function in class as well. So I hope you enjoyed this. Hope this was helpful. Take care and have a great day, folks.